Hello and welcome to all students. Students, we are in the topic of chemical bonding, and in this chapter, in our today's lecture, we are going to learn a new concept from this chapter, that is directional properties of bonds. Students, as earlier we have already learned what is meant by covalent bond and how that bond is going to be formed. The covalent bond is formed by overlapping of atomic orbitals. The molecules of hydrogen is formed due to the overlap of 1s orbitals of hydrogen atom and their formation and their energy graph also we have learned in previous slide. The valence bond theory explains the shape, the formation and directional properties of bonds in polyatomic molecules like methane, ammonia, water, etc. In terms of overlap and hybridization of atomic orbitals, we have already seen their examples, their formation, and the overlapping of atomic orbitals will be takes place on the basis of following things. When the orbitals of two atoms come close to form bond, their overlap may be positive, negative or zero depending upon the sign, that is phase and direction of orientation of amplitude of orbital wave function in space. The criteria of overlap as the main factor for the formation of covalent bonds applies uniformly to the homonuclear, heteronuclear diatomic molecules and polyatomic molecules. We know that the shapes of CH4, ammonia and water molecules are tetrahedral, pyramidal and bent respectively. It would be therefore interesting to use valence bond theory to find out if these geometrical shapes can be explained in terms of orbital overlaps. That now we are going to learn in this next slide. For the sake of our simplicity, we have considered the methane molecule, that is CH4 molecule. The electronic configuration of carbon in its ground state is 1s2, 2s2, 2p2, that is as its atomic number is 6. Here the number of electrons are present in it are 6. Number of protons as well as number of electrons are having the same number as well as we can write the electronic configuration will be like this, that is the nearest stable element electronic configuration of carbon is helium. So we have written their electronic configuration as like this, that is He 2s1 2p2, which in the excited state becomes means one of the electron from 2s orbital will enters into the last, that is 2pz orbital, and the electronic configuration will becomes like this 2s1 2p1x 2p1y 2p1z. That is one of the electron from 2s2 orbital will enters into the z orbital of p, that is 2p1z. The energy required for this excitation is compensated by the release of energy due to the overlap between the orbitals of carbon and the hydrogen. The four atomic orbitals of carbon, each with an 1 unpaired electron, can overlap with 1s orbitals of 4 hydrogen atoms which are also singly occupied. This will result in the formation of 4 CH bonds. It will however be observed that while the formation of 3 p orbitals of carbon are 90 degree to one another, that is if we consider the 3-dimensional spacing of these hydrogen atoms, they are present at the 90 degrees of each other. It will however be observed that while the 3 p orbitals of carbon are at 90 degree to one another, the HCH bond angle for these will also be 90 degree, that is 3 CH bonds will be oriented at 90 degree to one another. Now the 2s orbitals of carbon and the 1s orbital of hydrogen spherically symmetrical and they can overlap in any direction. Therefore the direction of the fourth CH bond cannot be ascertained, means this bond is formed in between the x, y and z axis. This description does not fit in with the tetrahedral HCH angles of 109 degree, 9.5 degree or we can also say 109.28 109.5 degree, or we can also say 28 minutes. Clearly it follows that simple atomic orbital overlap does not account for the directional characteristics of bonds in CH4. Now this is a slide which explains the overlap of the orbitals between P and P, and sometimes SP, sometimes the overlap is taking place out of the plane, on the axis, above the axis. All these points we have cleared in this slide. If we consider here, the positive overlap will take place like this, that is PZ orbitals of having the positive lobes are going to be combined. At the same time, if we consider here, the positive part of the node will combine with the negative node of the another PZ orbital, which turns in the formation of, or we can say the which in terms formation will takes place according to the negative overlap. And here if we consider here the second case, here PZ orbital of one molecule will combines with the S orbital of another atom, and this overlap is taking place linearly. So this overlapping we are calling it as a linear overlap of orbitals. But here some examples are also present, means their overlapping will takes place out of the axis. Such a overlapping we are calling it as a lateral overlapping. In that case, px orbitals are now going to combine sidewise. Such a overlapping is also called as a sidewise overlapping. Here there are two types in which the overlapping is now going to be takes place. Two positive lobes are going to be combined, and in the second case the negative overlap will takes place when positive lobe of one atom gets combined with the negative lobe of the another atom, means their orbitals px orbitals are combining in the lateral form but with the negative lobes. And here the same thing is also happened in case of py and py negative overlap. Here the zero overlap will takes place when the s orbital will combines with the px orbital, that is laterally. Such a case is also shown here in case of positive overlap and in case of negative overlap. Now students, we are moving towards the next point, that is types of covalent bonds. The covalent bonds can be divided into two types, sigma and pi bonds. How they are going to be formed and in which examples where sigma bond is going to be formed and where pi bond is going to be formed, that now we are going to learn in our next slides. First of all, we will understand what is meant by sigma bond. A sigma bond, this is the type of covalent bond which is formed by the end to end, that is head on overlap of bonding orbitals along the internuclear axis. This is called as head on overlap or axial overlap. This can be formed by any one of the following types of combinations of atomic orbitals. Now sometimes question may be asked here, when do sigma bonds are going to be formed? Answer for this question will be like this: when there is overlap, that time orbitals undergoes overlapping and hence any one of them are formed. Types of sigma overlappings: SS overlap, SP overlap and PP overlapping, in which there is a formation of sigma bond is going to be takes place. In this case, in SS overlap, there is a overlap of two half filled s orbitals along the internuclear axis. Means if we consider here the formation of s orbital of one atom when going to be combined with s orbital of another atom, that overlapping is takes place on the axis. Therefore, such a overlapping we are calling as the internuclear formation is going to be takes place on the axis. So s orbital will form on the internuclear axis. And the second thing is that sp overlap. This type of overlap occurs between half filled s orbital of one atom and half filled p orbital of another atom. Now here the third thing is that pp overlap. This type of overlapping takes place between half filled p orbitals of the two approaching atoms. That is, here we can take the example of px px, py py or pz pz overlapping. But the only one thing is that in the pp overlapping, sigma bond is going to be formed when the overlapping is takes place along the axis. This is the one and important condition which it should be followed. Then we can say that there is the formation of sigma bond along the axis. Now student, this is the overlap which is we have already seen in our previous slide. SS overlap is going to be takes place on the along the axis, and SP overlap is also you can see in the second picture, and in third picture I have already explained here in the previous slide. This type of overlapping is going to be takes place along the axis. In the formation of pp overlap, px px, py py and pz pz, only one there is a possibility is present where the formation is going to be takes place along the axis and there is a formation of sigma bond. So these are the different cases in which sigma bond is get formed. Now students, we are moving towards the next point, that is pi bonds. What is meant by pi bond and how they are going to be formed with some examples. Their concept we are now going to be see in detail. In the formation of pi bond, the atomic orbitals overlap in such a way that their axes remain parallel to each other and perpendicular to the internuclear axis. The orbitals formed due to the sidewise overlapping consists of two saucer type charged clouds. Look at this figure, you will notice here. These are the two lobes where they have the shape like saucer type of charged clouds above and below the plane of the participating atoms. And this is nothing, these lobes are having the electron cloud. So we have taken or we have explained their shape will be like this, and this is a part where the electron finding of electron is maximum. Such a part we are calling as the lobes. Strength of sigma and pi bonds. Basically, the strength of a bond depends upon the extent of overlapping. Students should take into account this point. This is a very important part where the strength of bonds depends upon the extent of overlapping. In case of sigma bond, the overlapping of orbitals takes place to a larger extent. Hence, it is stronger as compared to the pi bond, where the extent of overlapping occurs to a smaller extent. Further, it is important to note that in the formation of multiple bonds between two atoms of molecule, pi bond is formed in addition to the sigma bond. Means there are several cases such as, for example, in formation of acetylene, like such a molecules where the triple bond is present. In that case, sometimes there is a mixture of bonds are present. Both bonds, that is sigma bond and as well as pi bonds, are going to be formed. So this is the very important point that we will clear in the formation of acetylene or some different examples which are related to it. Now students, from this our chapter, there is a important points, along with there is a some examples are also present that we will look at in details sidewise. So the next part of our chapter is nothing but the hybridization. Pauling introduced the concept of hybridization. According to him, the atomic orbitals combine to form new set of equivalent orbitals which are known as a hybrid orbitals. Means by combining the atomic orbitals, there is a formation of a new equivalent having equivalent energy, or we can say the new set of equivalent orbitals, that we are calling it as a hybrid orbitals. Unlike the pure orbitals, the hybrid orbitals are used in bond formation. The phenomena is known as hybridization, which can be defined as the process of intermixing of orbitals of slightly different energies so as to redistribute their energies, resulting in the formation of new set of orbitals of equivalent energies and shapes. Such a orbitals or such orbitals which are going to be formed under the process of hybridization, or we can also in simply words say mix. This is nothing but the process of mixing and recasting of atomic orbitals so as to form the set of new energy orbitals are called as, and that process is called as a hybridization. For example, we are going to take the two examples, that is, for example, when 1 2s and 3 2p orbitals of carbon hybridized, there is a formation of 4 new sp3 hybrid orbitals. Now, what are the different salient features of hybridization that we should know before going to their examples? The number of hybrid orbitals is equal to the number of atomic orbitals that get hybridized. The hybridized orbitals are always equivalent in energy and shape, as earlier we have already explained. There means during the hybridization, mixing and recasting will take place, but the energy of the orbitals which remains same. The hybrid orbitals are more effective in forming stable bonds than pure atomic orbitals. Means after the formation hybridization is after the formation of hybrid orbitals, the orbitals which are going to be formed has the more effectiveness than that of the original ones. These hybrid orbitals are directed in space in some preferred direction to have minimum repulsion between the electron pairs and thus a stable arrangement. Therefore, the type of hybridization indicates the geometry of the molecules. Means hybridization will decide the geometry of the molecule which is going to be formed. Now, there are different important conditions of hybridization is there. The orbitals present in the valence shell of the atom are hybridized. The orbitals undergoing hybridization should have the almost equal energy. Then only hybridization will takes place. Promotion of electron is not essential condition prior to hybridization. It is not necessary that only half filled orbitals participate in hybridization. In some cases, even filled orbitals of valence shell take part in hybridization. So, students, there are different types of hybridizations are also there. That part is now we are going to learn in our next lecture. So, this is all about today's lecture. Thank you very much.